Hello, my name is John Lee, and I'm the president of Alpha Training and Consulting, and I have a true passion for preparing students for ASQ certification exams. But today, what we're going to be doing is we're going to go over some practice exam questions for the ASQ CQT certification exam. We're getting those questions from the CQT Primer, which is published and distributed by Quality Council of Indiana. Talk about a great company, a great group of people, and they have given us permission to use these questions in this video, and we greatly appreciate it. We use their great primer in our CQT online class. What we have you do is listen to all our lectures, take some exams, and then at the end of the class we have you review the primer, and we go through all the questions in the primer with you like we are going to in this video. However, in this video we're just going to do one or two questions from each chapter. If you're interested in that online class, just go to www.asqcqt.com. Again, that's asqcqt.com. That's a website dedicated to the CQT certification. And I answer all kinds of questions there concerning the certification exam. So again, if you have time, please listen to that. Other than that, let's move forward and answer some of these practice exam questions for the CQT. Facilitators will normally act as group leaders. No, leader and facilitator play two different roles as far as the ASQ exam goes. A leader wants to get things done on schedule, blah, blah, blah. All that stuff is very important, but a facilitator will say, wait a minute, slow down. We have to get everyone's buy-in on this. We have to create ownership or it won't work. And so even though you do have to meet deadlines, you need to start up front by creating buy-in. A facilitator gets everyone involved, which creates buy-in. ASQ loves facilitators, remember. So the answer is going to be very positive. Facilitators will normally act as group leaders. No. Summarize group ideas. They do summarize group ideas. There's no doubt about that. Limit feedback to the group. No, that's a negative. Facilitator is very positive. Limiting feedback is bad. So C is out of there. Function as a team recorder. No, they usually have other people doing that. Now, I don't really like any of these answers, but of all the answers, the best one is summarize group ideas. Again, I don't really like that. I think you could have a better answer than that. But compared to all the other ones, it's the only one that can work. So 2.5 is B. That is correct. Upper management typically supports the team process best by, remember, in ASQ, upper management, ASQ realize they're very, very busy. They don't have a lot of time to spend on your specific job. That's why they hired you. So upper management typically supports the team process best by giving them resources, my guess. Reinforcing positive team results. Yes, that would be a good one. I'm not going to throw that away. Punishing negative team results. No, ASQ does not like punishing people. So B's out of there. Providing unlimited direction and support. This unlimited, no one has unlimited resources. So providing unlimited direction and support, I have a problem with. So I think I'm going to throw that one away. Allowing but I could be wrong. Allowing teams to establish the company's mission statement. No, upper management creates the mission statement. So that one's out of there. So reinforcing positive results, and then C, providing unlimited direction and support. I like A and C. I have a big problem with unlimited direction. Upper management typically supports team process best by reinforcing positive team results. I think I'm going to have to go with A, but this is another one that's rather difficult. 210 is A. Process control charts are used mainly to do what? Identify special cause variation is one possibility. Portray process status. Yes, that's true. That's a very general answer. I like it. That's probably the correct one. Classify process characteristics. No. Illustrate process deficiencies. No. I mean, it could be. Identify process peculiarities. Yes. So they're all correct. That's the problem. But which one is the most general? And it's A, portray process status. So this is one of those ones where they're all correct, so we pick the most general. 3.2 has to be A, and that is correct. If 87 data observations from a process were to be plotted on a histogram, the rule of thumb would suggest which of the number of intervals across the range of data. Okay, and you can look this up, but I'll tell you what it is. It's a rather common question on an ASQ exam, so you'd be wise to remember this, make notes, and this is how you do it. Said 87 observations. So what you do is go put in 87, and then you just take the square root of that. The square root is this button right here. See that? Square root button. Click that, and it's 9.32, so the correct answer is going to be 9. It's the square root of the number of observations is the number of categories they recommend you use on a histogram. So again, this one will be 9, and that is D. So 3.3 is D. Let's see if that's correct. It is. What is the standard deviation of the following complete set of data? I'm glad they gave us another one of these because it says complete set of data, meaning this is a population. Maybe this is the weight of some animal that's about to go extinct, and there's only 5 of them in the whole world. So this is the whole population. And so when I calculate the standard deviation, it'll be the population standard deviation. So let's go ahead and do that. And I need to get this. You should know how to do this by now. So I'm not going to go in any great detail since you already know how to do this one. You go 3.2. Well, first clear it, shut it off, start it to make sure everything's cleared. 3.2 summation, 3.1 summation, 3.3 summation, 3.3 summation, 3.1 summation. It says there's 5 there. 1, 2, 3, 4, 5. That's correct. It makes me feel a little better. Now I'm going to go second function. And this time I'm going to go division because that's population standard deviation. And it gives me 0.08944. 0.08944. That is B. 4.4 must be B. And it is B. So very good. In a normal distribution, what is the area under the curve between 0.7 and 1.3 standard deviation units? Okay, this is always hard for students. You may write down on your notes there 0.7 to 1.3 because I'm going to take this off. And we're going to look up 0.7 to 1.3. First, I'm going to draw it out for you. So what they're asking for is they say they have this normal distribution. Now I'll start down here. Normal distribution. There we go. And they want to know that if you go out 0.7 sigmas, right there, and 1.3 sigmas, I'm going to have to change this a little bit. I don't like to do that because then I have to set it again. But we have to be able to see what we're doing. So it says if you go out 0.7 sigmas and then out 1.3 sigmas, I'll make that a sigma there so you know that. It wants to know the area between those two. So it wants to know this area, this strip of area right there. So what you'll do is you'll go to the Z table, you'll look up 0.7 and see what lies beyond this. Then you'll look up 1.3, see what lies beyond this, subtract the two, it'll give you the area of that strip. It's kind of difficult, I know, but it's also a fairly common question. So I want you to be able to do it. So first I'm going to look up 0.7 here in my Z table. There it is, 0.7. That's hard to read, being so small, but it says 0.242. You should pull yours out, maybe put this on pause. Make sure you know, okay, 0.7 is 0.242. So I'm going to come back to my drawing here, and I'm going to put in parentheses that from 0.7 sigmas out further out, it's 0.242. Just going to write 0.242 right there. Then I'm going to look up 1.3 sigmas. So I'm going to go to my Z table and look up 1.3. 1.30 right there is 0.0968. 0.0968. 0.0968. I had to write over my curve there. And what I'm going to do is I'm going to go 0.242 minus 0.0968. That'll give me this strip of real estate right there. So let's do that. Pull out my trusty calculator here and go 0.242 minus 0.0968 equals. And that's 0.1452, which should be the correct answer, 0.1452. And there it is. I saw it as I put it down there. But let me blow this back up again and focus it for us. And there's 4.7 right there, and 0.1452 is D. Put my answer sheet down here. It's D. So if you need to rewind and listen to that again, please do so, but I want you to be able to get that one right since it's fairly common. So 4.7 is D is correct. Today we're going over Chapter 5 of your primer, which is control charts. Now, when I heard we were doing control charts today, I took out my favorite pages on control charts. And if you have these 2 pages out of your primer, it's probably the only 2 pages that you'll need. So let me show you those. This is from the appendix here, and this is for variables control charts is what we're going to use this one for. And I'm going to take this out a little bit so we can see the whole thing. It's going to be so small you can't see it probably, but at least you'll know what page I'm talking about. And so this is for the variables charts, has all the formulas down here. Here's for X bar R charts. Note it says control limit for X bar. That's an X bar down there. I know it's too small to see, but then it has the formula there. X double bar, which is the average of the averages, plus A2 times R bar. Notice it says plus minus, and it doesn't say upper control limit here. So for upper control limit, you add A2 times R bar. For lower control limit, you go minus A2 times R bar. So it's just a different way of writing the formula. Here's the upper control limit for the range, lower control limit for the range. Here is the X bar S control limits that you need there, and approximate capability. This is, I don't know why they call it capability. That's an estimate of standard deviation, R bar over D2. Remember that formula is for single events. And approximate capability, S bar over the C variable there. You can also estimate sigma off that. I've never seen them use that in the test. They always test you on this, very common. Here are all the constants you need for your variables charts. And so for variables charts, this is probably about all that you'll need. Now let me show you another one that is definitely one of my favorites. As soon as I can find it here. There it is. This is a very, very wonderful page out of your primer. And as you can see on the revision I'm using, and this may change now, but it's 16. The last page I showed you was from the appendix, by the way. You get that out of the appendix, and it's page 12 of Chapter 7, at least on the revision I'm using. Yours may change by the time you look at this. But they always give this same chart. I like this one. Why? These are for the attribute charts, the P charts, the NP charts, the U chart, C chart. And why do I like this so much? Well, this column is for when sample size is fixed. So if sample size is fixed and you're working with defectives, you use the NP chart. If sample size is fixed and you're working with defects, you use the C chart. And here's all the formulas for the C chart, all the formulas for the NP chart, everything you need there. And of course, if sample size varies and you're doing defectives, it's going to be the P chart. If you're going to use sample size varies for defects, you're going to use the U chart. It also gives the distributions. So if you're working with defectives, you're going to use the binomial distribution. They're going to ask you those types of questions. This is a wonderful page. It's one that I ask you to put in your critical stack. Okay? And of course, if you're plotting defects, either one of these charts here, it's going to use the Poisson distribution. So very powerful, powerful page here. One of my favorites. So as we go through the problems, I haven't looked at them yet, but I know we're going to need those 2 pages. Now, as an alternative, you can also go to your instructor notes. And we have one for attribute charts. And it talks what distribution, fraction defective, then it gives all the formulas there. So similar thing, if you feel more comfortable with this one, that's fine. Here's kind of a flow chart down here to help you also. A student created this one for the other students. So that was awfully nice of him. And students have been using it quite a bit. So it just depends, preference. I wanted to show you the options. Here's another one. This is out of your white book also in the appendix. There's your X bar R charts. There's all the formulas for upper and lower control limits, range chart, X bar S charts, etc. And here's all the control chart factors you'll need. And then there's some English, Greek alphabet characters. It goes over those a little bit. But for this, this is where you use the variables chart information, and this is what you'll use the SPC chart information, or for attribute charts, all the information. So whichever pages you desire to use, there they are, and you can just use those 2 to give you pretty much everything you need in SPC. Now, SPC is also going to test on the central limit theorem, and that's going to be the one that's most difficult for most of you when they ask those types of questions. But let's move forward, and we'll work through them one at a time. In this one, excuse me, in this one, what we have is they have 36 questions. So I'm going to do half of them. I'm going to do 18 in this session, then I'll leave the other half for you to do. So let's look at our first question here. I think I can blow that up just a little bit. It's not going to hurt anything. I like to have 3 questions I can work off there. And this one actually is at 4, so I'll take that also. All right. A process which is in statistical control. What does statistical control mean? It means the process is in control. What does that mean? It is predictable. Why is that important? Because if it's predictable, we can do math. If it's not predictable, you can't create an SPC chart. So that's a very important thought right there. A process which is in control will produce product to specification. No, I said it was predictable. It may be predictably bad, may be predictably good, may be predictably acceptable, but it does not mean it falls within specs. Produce product to specification, that's not statistical control, that's capability. Be sure you understand the difference between those 2, or else you're going to have a struggle in the test. So let me tell you again. Statistical control means it's predictable. Capable means you can produce it, the product, within the specification limits, within a proportion or a probability that's acceptable to the customer. Okay, so it's not that one. B, consistently produce product which, when charted, will fall within statistical control limits. This is true. That is true. And my guess is that's the correct answer. Now, result in a CP value of 1.0 or better. No. Because this is just telling you when the SPC chart tells you when something's changed, when you have special causes come in. Do not, let me just put it this way, do not compare SPC to spec limits, because SPC usually plots averages, which shrinks the distribution. Well, if I increase average enough, I can get pretty much the vast majority of my probability to fall within the upper and lower control limits. So this is the rule I want you to remember, even if you don't necessarily understand it. Do not compare SPC control limits to spec limits, because you're using averages usually. And so, and it's not for single events. CP is for single events. It uses single event standard deviation. So you can't compare CPs to SPC. They're two different worlds. SPC, they have two different, totally different objectives. SPC tells you if it's in control, which means it's predictable. CPK values tell you if it's capable. But you can't do CP values calculations until the process is in control. Remember, you do no math. You do no math unless the process is in control. You can't, because it's unpredictable. You can't do math on unpredictable things. Now, I know I shared a lot of stuff with you here, but hopefully it helps. D, result in very narrow process spread. No. No. Just because it's in control doesn't mean that it's going to have a short process spread. That's capable. This is about capability. D is. C is about capability. A is about capability. So they're trying to see if you know the difference between capability and in control process. And the only one that talks about control is consistently produced product, which when charted will fall within statistical control limits. They could have made it a little better, say fall within statistical control limits 99.73% of the time would be more correct. But of all the options here, B is the only possibility. I'm going to check my work anyway, but yes, 5.1 is B, so we're in good shape. What is the upper control limit for a P-chart, proportion defective, when the average daily production is 25 units with an established fraction defective of 0.05? All right, so this isn't going to be hard. We'll have to go to the whiteboard, and first you have to find the formula. Well, P-chart is in an attribute or a variable chart. It's an attribute chart. So I'm going to pull up the attribute chart page, and I'm taking the one out of the primer. This is one of my favorite, if you'll recall. I love this little table here. And it says a P-chart, and there's the upper and lower control limits right there. P-bar plus 3 times square root of P-bar times 1 minus P-bar over the square root of n. Notice this is 3 times sigma here, so this is the sigma of the binomial distribution. That's why I like this chart. It gives you so much information. It's just wonderful. And they give us all the information we need here. They gave us N of 2,500, and I think P-bar was 0.05, if I remember correctly. So all we have to do is put, if it is 0.05, I'll check it again here in a little bit, but put 0.05 there, put 0.05 there, put 0.05 there, put 2,500 here. And so let's make sure my numbers are correct, and if they are, then I'm going to start putting them in here. Yes, it is 0.05. We only need 2 numbers. We need the sample size and the fraction defective. There they are, 0.05 and 2,500. So you may want to write that down. In the meantime, I'm going to come back to this formula, because I know what most of you are going to have problems with as a quality technician, and that's order of operations. So you may want to mark on this if you have order of operations and say, do this first, do this second, etc. The first thing you're going to do are these parentheses right here. And it's going to be 1 minus P-bar. Do you remember what P-bar was? It was 0.05. So I'm going to put my calculator right here. Yeah, that works out pretty good right there. And I'm going to go 1 minus 0.05 equals. So that is what I do first, that parentheses right there. 1 minus P-bar is 0.05. You always do parentheses first. Then I'm going to multiply by P-bar. Remember, P-bar is 0.05. We work with 0.05 a lot in this formula. It's almost everything except for sample size there. Of course, we have the constant 3 also. So now I'm going to go times 0.05. So let's go back to the calculator. Times 0.05 equals. Okay. Now, I've calculated this P-bar times 1 minus P-bar to be 0.0475. Then I'm going to divide by the sample size, which is 2,500. So I'm going to go divide by 2,500 equals. Okay, now I've got all of this done within that square root sign. Now I'm going to hit the square root button, which is right here, and that'll get us through that portion. There I go, square root, just pushed it. And what do I end up with? 0.00435. So that's everything. I did everything in the square root. That's what you want to do first. Then I'm going to go times 3. Times 3 equals. So that's that 3 times sigma is this value right there, 0.013. Now, you should write that down because it'll be easier when you do the calculator, because I'm going to add this to P bar for upper. I'm going to subtract it to get the lower. So I'm going to write this down so I don't have to recalculate it. 0.01307. I know you can't see where I wrote that down, but you should be writing it down also. And how far do you go out? I like to go out plenty distance, because but really 0.05 you should be able to go out. Just I'd go out 4 at least, but I went out more than that because I'm kind of cautious this way. Okay, I'd rather have more than less. It just makes it more accurate. And okay, there we have it. Now I'm going to do the upper control limit. Now that I know 3 sigma here, I'm going to go plus P bar, which is 0.05, so I'm going to go plus 0.05 equals. That is my upper control limit. Upper control limit for the P chart is 0.063076697. There you go. Now I'm going to take this off, and I'm going to look and see if that gets me what I need there. Yeah, because we only asked to calculate the upper control limit. Sometimes they'll ask for the upper and lower control limit, but you look at the upper control limit. If there's no repeats, you only have to do the upper control. If there's no repeats there, and you can ignore the lower control limit at that point. But if there is a repeat, the same value for upper control limit, and then they switch it on the lower, you're going to have to calculate both. But this one, again, was just upper control limit, so that's 0.063. 5.3 is C, and thus it is C. So there we have it, 5.3. We're into it, and we have 100%. The surface plate is essential to precision mechanical measurement because it provides. Okay, a surface plate provides a flat surface, and it's even calibrated. These surface plates need to be calibrated. There's granite ones and there's iron ones. They both have their advantages and disadvantages. They'll ask you that on the test. What's the advantage of the iron one? Well, the iron one, it's magnetic, so you can magnetize your instruments and clip them down there and hold them steady. That's the advantage. The disadvantage of the cast iron is it tends to corrode. And of course then we have the granite, and you can really make those awfully flat, so they're very good and they don't rust. But they also they're not magnetic for your magnetic based measuring equipment. So there you go, that's just off to the side there, but that's what we're talking about. The surface plate is essential to precision mechanical measurements because it provides a reflecting surface. No, it doesn't have to reflect light. An accurate reference surface, yes, that's what it's all about. A wear resistant, I mean, that's nice, but that's not its purpose. A vibration proof work surface, not necessarily. You could hook some big vibration machine up there and make it vibrate, I'm sure of that. So it's going to be an accurate reference surface. Remember I said they had to be calibrated? Calibration is to accuracy. So it's going to be B. 6.7 is B, and that is correct. Surface tension of a liquid can be measured using and I know this one, tensiometer is the correct answer. 613 is C. That's not very helpful, but what can I say? It's a lookup question. Test and measurement equipment found out of tolerance at the end of a calibration cycle could indicate several problems. The best course of action to be taken under these conditions is, key word here, best course of action, key phrase I guess I should say, best course of action. Remember, ASQ does not like to take risk. So review for possible effect on product already inspected by the equipment. Yes, you should do that. That is very important because you may have checked some and your calibration's off, so you may have let bad product go. So you're going to bring everything's back that is impacted and check to make sure it's all right. I like A. B, calibrate the equipment with no further action. No, that is too much risk in an ASQ world. Recall all product and reinspect after calibration. Yes, I like C. I really like C. So, but the problem is it's very close to A. Review for possible effect. Recall all product. Recall all product I don't know what they're talking, but if they're talking all product that your company has ever made and you have 200,000 employees, you're going to go broke if you recall all product. So that concerns me a little bit. I'd rather review for possible effect is a better word than recall all product. So I think I'm going to go with A for that reason. Disregard, since this does not happen very often, no. Definitely B and D are out of there. It's between A and C. I told you the reason I like A, so let's go with A. 7.1 is A, so we've got a good start. Thank goodness. This is usually a hard test for me. I've failed it many times. Not this specific one, but test questions on this chapter. Calibration certificate should indicate the environmental conditions during the calibration process under all circumstances. Usually I don't like all, but temperature is pretty important in calibration. I'm not going to throw it away quite yet. It could be the correct one. Only when calibrating in the field? No, I can already throw that one away. I don't even need to read the rest. When the technician believes the conditions were out of range, feels, that's gut feel, subjectivity. ASQ isn't going to like that. C is out of there. In an ASQ exam, that's out of there. So A is the best so far. When the environmental conditions can have an influence on the results, yes. That's when you want to write down temperature instead of all. This is a much better answer. 7.2 is D, and that is true. And Chapter 8 is about blueprint reading. So there'll be some GD&T. You should have already taken those modules. If you have, this one should go fairly well for you. Let me show you the pages I use for this chapter that's most common. One is, at least on the revision I'm working from, is, where is that? Let's show you the page number. Chapter 8, page 15. And it will show you the screw thread, the angle, the crest, the depth, the major diameter, minor diameter, pitch. Pitch is the distance from a point on one thread to the same point on the next thread. So it shows pitch right there, showing you that because it's the first question on our exam we're going to go over. But this is a very helpful page. And if you turn this page over and go to page 16, this is also something I use a lot. It will, because they'll give you the symbolism and ask you to interpret what they are. And one thing that always helps you is, let me see, thread class, thread series. Seems like one was internal and external. Oh yeah, there it is. Internal or external, right there. And I can't remember which one is A, which one is B. But that's a common question. You need to know that. And I'm looking for it here. Maybe it's not going to tell us. Oh, yes. Many drawings will omit the A. So I'm just going to read that because it's so common. Thread class symbol. This symbol tells how tightly and matching internal and external threads fit together and whether the specific thread is external, such as a bolt, or internal as a nut. A Class 1 fit is the loosest fit. Class 3 is the tightest fit. The letter A following the class specifies external. There you go. So A is external, B is internal. And so that is always showing up. I haven't looked through these questions today, but that's a common question anyway. Now, the other page that I use are these symbols, 18. These are just some symbols of surface roughness, etc., and parallel, perpendicular. Anyway, all these various symbols, I use that a fair amount. And this one, of course, I use all the time. This is the GD&T symbols, and so we'll be looking at those. Also, I'm sure they'll test us on those. So those are the pages I use. By the way, that's on page 19 of the revision I'm working off of. Okay, with that being said, let's move forward and see how we do on this. And I did look at the first question, and guess what? It's about pitch. That's why I told you about pitch from that drawing I had up here. The distance from a point on a screw thread to a corresponding point on the next thread measured parallel to the axis is called, and I already showed that one, it's thread pitch. So 8.1 is B, and that's correct. 8.2, by the way, there's only 28 questions on this one, so it won't take us too long. So we'll do 14, we'll leave the last 14 for you. Related to geometric tolerancing, GD&T, the supporting datum plane that must be contacted at 3 highest points on the surface is the primary datum. So remember, primary has 3 points, secondary has 2, tertiary has 1. And if you have a primary, secondary, and tertiary data, you can stabilize the part so it can't twist during measurement. But 3 points is primary datum. You'll need to know that. Primary datum 3, secondary datum 2, tertiary datum 1. And so this will be the primary datum A. 8.2 is A. Let me look at it here. Where's it? Oh, there it is. Yes, that is correct. True test variability can be obtained in a destructive testing situation. Notice it says true testing variability in destructive. Destructive means you test one, it's destroyed, you can't do anymore. So can you really get true testing variability? No, you can't. Obtained in a destructive testing situation under which of the following conditions? I already know it cannot be obtained, so it has to be B. 9.1 is B. So this can be a challenging chapter. I'll take a start with 100% here. 34.4 and 56.18 are multiplied together. Okay, so I need to pull out the calculator here for a minute. Here it is. So I'm going to go 34.4 times 56.18. And it equals this, 1932.592. But we did a multiplication manipulation on this thing, so I need to know how to round it. Well, the way you do that, as I understand it anyway, you take the one with the least amount of significant figures, which would be 3. This has 4, this has 3, and add 1. So I'm going to do 4. So 1, 2, 3, 4. I'm going to take it right there. I'm going to round it up. 0.592 is going to round this up to 3, and it's going to be 1933, following the rules of rounding. And that is C. So 9.2 is C. That is correct. So remember, find the one with the lowest number of significant digits, add 1 to it, and that's what you round off to when you do the math. Which of the following non-destructive testing methods is best for rapid inspection of half-inch diameter carbon steel rods? Now there's a lot of lookup questions in this one also. We've had a lot of lookup the last 3 chapters, I think. But the quickest one for surface cracks, radiography, that is X-ray, and that isn't going to be the most time-efficient method. Ultrasonic, no, that takes quite a bit of time. Magnetic particle, yes, that's pretty quick. Liquid penetrant, no, that's very slow. And it says, which of the following non-destructive methods is best for rapid? Rapid is the key word. So I'm going to say magnetic particle. You can look that up in your table if you need to, but I know that to be the case. 9.3 is C. That's right. 10.1, product quality audits are useful for pre-award surveys. Now, you have to remember a product audit is something very specific. Product audit, the key words are you use a very small sample size. Very small sample size. But you do a very thorough job. So you'll tear these parts down and you'll check every dimension and make sure it's in spec. So it's very thorough, very small sample size. It's customer oriented. If you didn't know that, please make note, whether it's mental or on a piece of paper, so that you can remember it. Again, product quality, small sample sizes, very thorough, customer oriented or directed. So that's what we're talking about here. Product quality audits are useful for pre-award surveys? No. Are based on statistically sound sampling? No. The samples are too small. Can be used in place of inspection? Of course not. Should be customer oriented? Yes. That's one of the key words, remember, is customer oriented. So 10.1 is definitely D. I looked that up and that is correct. Quality audits will provide answers to quality system deficiencies? No. They do not provide answers. As a quality auditor, you should not give answers to deficiencies or recommended solutions unless given permission from the client, but usually that's not the case. You just say, this is what's wrong, You guys go figure out how to fix it. So A is out of there, very much out of there. Highlighting of faulty company operations. Okay. Yes, that could be. Usually SQ doesn't like to get that negative. Faulty seems a little aggressive for an ASQ exam. But I'm not throwing it away, because it is true. Information on unnecessary quality standards. Why would you give information on something that's unnecessary? So there's something wrong with that one. I throw that one out right now. A guaranteed customer acceptance of the product. No, guaranteed is an absolute. You can't guarantee too many things in life. So D is out of there, and that left me with which one? B. So it has to be B. It's not my favorite answer, but it's the best of the options, and that is correct. Which of the following improvement terms is considered revolutionary in nature? All right, I already know which one it is. So it's the most aggressive one. And what is most aggressive? Re-engineering. So just remember this, a key word. You shouldn't have to look this up. The most revolutionary is re-engineering. What is re-engineering? You take the shop floor, you wipe everything out, you mop the floors, you paint the floors, whatever, and you start from scratch with all the newest technology. You implement new technology based off all the information you've gathered over time, your knowledge and wisdom, and you make it much better. You're not trying to fix something that's broke. You're just starting over fresh. And so that's re-engineering and breakthrough achievement. It is the most revolutionary. And so I don't even need to read the rest of them, to be honest with you. It's going to be B. But Kaizen, Poka-yoke is mistake proofing. Kaizen is slow, incremental improvements over time. So that's not so revolutionary. It's rather slow. Kanban and mistake proofing. Kanban is part of the visual factory to control inventory flow. We know mistake proofing is same as Poka-yoke. Containment and corrective action. Those are good, but they're not that revolutionary. Definitely it's B. Remember that one. It'll help you get answers right, and it'll help you do it quickly. I could have just went to B immediately. 11.7B, yes, that is correct. Which of the following avoids waste by using SPC to maintain control of the process? Which of the following avoids waste? By using detection system, an avoidance system, a protection system, a prevention system. Well, in quality, the best word to use to cover all that would be prevention. But SPC, is it prevention or is it detection? It depends. Okay, it depends. Geez whiz. I know ASQ loves prevention. It's looking for a positive. They like prevention more than detection. They like SPC. I'm going to have to go with D on this one. 11.8 is D, but I thought that one was a little difficult. Because SPC can detect. Something already happens, and then you measure it, but you detect it, but hopefully you detect it before a problem occurs, and that makes it preventative. And that's the goal or objective of SPC. So that's why I went with that one, but it was a little tricky. Congratulations, you've almost finished this video. If you have any questions, please contact me. As you can see, I have a lot of experience in ASQ certification exams. I passed most of them myself. If you have any questions or would like to contact me, do so through my website at alphatc.com. Again, that's alphatc.com. Go to the Contact Us portion of the website. Send me a message. I'll get back with you as soon as possible. Hey, thank you, and have a great day. Goodbye.